Okay, we're going to look today at how to assign oxidation numbers. There's 3 simple rules that we can follow to calculate the oxidation numbers of an element, whether it's alone in the elemental state or included in a polyatomic ion. The first rule is very simple. Any element in its elemental form has an oxidation number of 0. So for example, if you look at metallic lithium, a solid piece of lithium, its oxidation state is 0. Fluorine gas, which is a diatomic gas, has an oxidation state of 0. The oxygen we breathe, O2, has an oxidation state of 0. Second rule, the oxidation number of a monatomic ion is the same as its charge. Example, lithium cation has a +1 charge, its oxidation state is +1. Fluoride anion has an oxidation state of -1. So the first 2 rules are very simple. The third rule has a few corollaries to it. So nonmetals tend to have negative oxidation numbers, and it stands to reason because they like electrons more than do metals, although some are positive, and certain compounds in certain compounds are ions. So if you put 2 nonmetals together, the more electronegative of the 2 is going to take the electrons away from the less electronegative of the 2, and the less electronegative atom will have a more positive or less negative oxidation state. Oxygen is usually -2, except when it's in peroxide, and you have 2 oxygen atoms stuck together, then it becomes -1. The only other element that can take electrons away from oxygen would be fluorine, the most electronegative element. Hydrogen is usually -1 when bonded to a metal, and it's usually +1 when it's bonded to a nonmetal. Hydrogen is sort of in the middle of the continuum. Depending on what you put it with, it either takes the electrons or it gives them away. Fluorine is always -1. Other halogens are normally -1 except in oxyanions. Again, when you combine anything with oxygen, oxygen is usually more electronegative, so it'll take the electrons away, and the other halogen will have a positive oxidation state. We'll see an example of that later. In neutral compounds, the sum of the oxidation state, the oxidation numbers is 0. So in lithium chloride, composed of lithium plus and chlorine chloride, which is -1, +1 and -1 will cancel out to 0. In polyatomic ions, the sum of the oxidation numbers is equal to the charge on the ion. So for example, in sulfate, the overall charge on the ion is -2. We know from the earlier rule that oxygen is usually -2, and there's 4 oxygen atoms, so that's going to give you a charge of -8. So how is it possible that if you have a -8, that the overall charge is -2? Well, that should tell you that there's something that has a +6, and because there's only one other element in the molecule, it has to be sulfur. So from that we would deduce that the sulfur has a +6 oxidation state. In ammonium, which has a +1 charge, we see that hydrogen, normally when it's with a more electronegative element, will have a +1 oxidation state. There are 4 hydrogen atoms, so that would give you +4. So how is it possible that ammonium has only a +1 charge? It has to mean that nitrogen is at -3 oxidation state. You'll notice if you look in the periodic table that a bunch of little numbers appear above the symbol for the element. Those numbers symbolize the possible oxidation states of the elements. You'll notice that, for example, in the alkali metals, they only will take a +1 oxidation state. The alkaline earth metals only +2. In the transition elements, you see several elements that have a whole host of possible oxidation states. For example, manganese has +6, +7, +4, +2, +3, and it'll also show usually one of the numbers in bold, which means that's the favorite oxidation state of the element. So manganese has +2 as its favorite oxidation state. The atom of iron prefers to have a +3 oxidation state. So the ferric cation is the preferred oxidation state of iron, although it's also capable of ferrous, which is +2. You'll also notice that with the non-metals, you have things like chlorine, which is capable of anything from 1 to 7, 1, 3, 5, 7, plus or minus, depending on what you put it with. And some of the chalcogens are also capable of the same versatility. Carbon also will go from ±4 to everything in between. So let's continue with some more examples. Permanganate, MnO4 minus 1 overall. It's got 4 oxygen atoms, each one with a -2, so that you should expect that it's -8, but it's only -1. So something is contributing +7. That means the oxidation state of manganese is +7. As it turns out, that's what it is in the permanganate cation. In the periodate series, if you start off with iodide, the oxidation state for iodide ion is -1, same as the charge. In the hypoiodite anion, you have one oxygen atom, with a charge of -2, but the overall charge on the polyatomic ion is -1. So something has to be +1, and that's the iodine atom to give you the overall charge. In the iodite ion, we have 2 oxygen atoms, giving you a total of -4, but overall the molecule is -1. So that means the iodine is +3. In iodate, you have 3 oxygens times -2 gives you -6. Overall it's -1, so the iodine has to be +5. And in periodate, you have 4 oxygen atoms giving you -8, but overall it's -1. That means the iodine is +7. So you see that it runs the whole gamut from -1 to +7 for the possible oxidation states of iodine.